Okay, so hi everyone. So this is the 10th week we are meeting for the course Fluid and Particle Mechanics. So in the last class we mainly talked about uh, the distinction between laminar and turbulent flow and how you can distinct like characterize the laminar and turbulent flow based on the Reynolds number, and then we discussed about the concept of critical Reynolds number and we then talked about the like uh, qualitative definitions of laminar flow and the turbulent flow and their characteristics, and then we discussed about the concept of eddies. Okay, and we discussed about the largest eddy and the smallest eddy. The largest eddy can be of the length scale of system length scale, and the smallest eddy is the Kolmogorov length scale. And we uh, like showed that the Kolmogorov length scale is of order this nu cube by epsilon the whole raised to 1 by 4, where nu is the kinematic viscosity of the fluid and epsilon is the turbulent dissipation rate. Okay, and so we talked about the energy cascade. So it's these derivations is based on that energy cascade theory, and then we show that there is uh, smallest eddy or the Kolmogorov eddy and the largest eddy or the system length scale can be related by this relation, and it is related with the Reynolds number based on the system length scale. Okay, so in this week, as we go forward, we mainly talk about the statistical description of the turbulent flow. Okay, so why the statistical description is required? Because as you know that in turbulent flow it's a random chaotic flow which involves lot of length scale and a lot of time scale, as we talk about it in the uh, last class. We have already discussed all this. These are the basic characteristics of the turbulent flow. Now it it involves the lot of length scale and the time scale, and also there are fluctuations. Okay, so today we will mainly talk about the statistical description of the turbulent flow. Okay, so here I will mainly, so first you need to understand that why the statistical descriptions are required, because in order to describe the turbulent flow you need to describe it in terms of statistics. Okay, because there are a lot of fluctuations present in the problem. For example, if u of x comma t is a velocity at any point of the turbulent flow. Okay, so u at x comma t can be decomposed into u bar at x comma t. Okay, so this u is a vector. Okay, let me write it in the vector sign only, then it will be easy to follow for you also. So u at x comma t I can decompose into two component, u bar at x comma t plus u prime also at x comma t. So this is the average or the mean and this is the fluctuations. Okay, so if I get a signal like this, let's say from an experiment I get a signal of the velocity which is something like this. Let's say this is my signal of the velocity which is something like this. Okay, so what I am plotting here, I am plotting u, the full velocity with time. Okay, so if this is my original velocity from some experiment, I will have, and let's say this is the mean of that. Okay, let me make it a thick color. So this is the mean. Okay, so what I am trying to say, that this red color is u bar. Okay, so what is the fluctuations then? So I will have some red bar. So you can see that the average is not changing with the time. Okay, so if the turbulent statistics are not, if the turbulent statistics are not changing with the time, then we will call it as a stationary turbulence. Okay, so we will call it as stationary turbulence. So this a red line is actually the time average of the original signal. So how will we define this time average of the original signal? So we can write it in this way. So let's say this is the, once again let me repeat it very clearly, that this is my velocity fluctuations, or this is my original velocity data from some experiment or maybe some numerical simulation, that I am getting that velocity as a function of time at some particular position. Let's say that position is some x vector. Okay, like this. So there I got that with time the velocity is changing in this fashion. So what I can do with this, I can calculate the time average of this velocity. So how can I calculate the time average of this velocity? So what I will write here is that, so I have u, so I will have u bar. So I am not writing any vector sign for the sake of simplicity. So I will calculating u at some position x comma t, u bar as the time average. So when I am calculating the time average, so 1 minute. So I have u at some position time, let's say that position is x naught comma t. So these I have. Okay, like what I will do, I will do the time average of this quantity. So when I will do the time average of this quantity, what will I have? I will have u, sorry, I am writing as u, so there will be no bar here, I'm sorry, yeah. So u bar at x naught, so it is the time average. So I can write it in this fashion, that it is 1 by delta t. Okay, then integration t minus delta t to t plus delta t, okay, into u at x naught comma t into dt. So this is the time average. So these equations indicates this red line. Okay, so if I see that the time average is not changing, so I'll just write it once again. So what this says, this says the time average of the velocity at location x naught. That's the definition. Okay, now here is the point. So if the time average is not changing with time, then we will call it as the stationary, statistically stationary. Okay, and if the turbulent statistics are not changing with time, we will call it as stationary turbulence. So you can see that that this delta t, okay, the turbulent fluctuations has very small time scale, and we can see that over a very short time it is having a very rapid fluctuations. Okay, so if we want to average it out, we must take a time scale which is much larger than the fluctuations time scale. So the fluctuations are taking place at small time scale because I am getting it as a signal. So the time over which I have to average it should be much larger than that fluctuation time scale. Then only I will be able to get these statistics, or this quantity will be statistically significant if I average over a time scale. That means the delta t should be, this delta t should be large enough. Okay, so that is called a delta t should be large enough with respect to the fluctuations time scale. Okay, and if the average doesn't change with time, then we will call it as stationary turbulence. So this is all about the time averaging. So this I will call it as time average. So what do you mean by time average? The time average means we are taking the signal or the original turbulent velocity at some point x over a time period, and then we are averaging it over time, and that time scale over which we are averaging it should be long enough compared to the fluctuations time scale in order to get that statistics correctly. Now we will talk about space averaging. So space averaging means what? So the space averaging means at a given time we are taking the data at different spatial location and finding. So time averaging means at a given location we are taking the data at different time and then averaging it out. But the space averaging is at a given time we are taking the data at different locations and then finding an average. Okay, so what will be the So if I get a similar signal at different positions, so instead of t in this axis, instead of this t, I will have x, some coordinate, and here it will be the u. So if I get a similar signal like this, then what will be my definition for the space averaging at a particular time instant t? So this space averaging at time t naught, here we are talking about the time averaging at location x naught. Okay, that was the coordinate. Now the space averaging should be a function of time. Sorry, space averaging should be at a particular time t naught. So what will be that? I can write it as integration 1 by integration 1 by v. So this is the, and it will be a volume integral over v. So it will be 1 by v integration v, then u is my original this thing. So u at x comma t naught into dt. So this is the averaging over space, or for a one single, like if I write it in terms of x coordinate, or if I write it in terms of delta x, so it should be something like that: u average at time t naught should be equal to 1 by, so here what I wrote, yeah, this is this 1 by delta t and this, right? Yeah, so here it will be limit delta x tending to 0, integration 0 to delta x, then u at x comma t naught into dt divided by delta x. Fine. So this is the space averaging. So it is the same concept. So this is for time averaging, that turbulent statistics are not changing with time. Here we are talking about space averaging, where turbulent statistics are not changing with space. Okay, that means at a particular time instant, if I take the data at different locations and the average them out, then we should average that according to this equation. That's what I'm saying. But in actual experiment, we usually are not very careful about time averaging or the space averaging. What we do intuitively in an experiment is something called as the ensemble averaging. Okay, so what do you mean by the ensemble averaging? So we talk about time average, then we talked about space average. Now we'll talk about ensemble average. Okay, so what do you mean by ensemble averaging? So the ensemble averaging is that if we do a large number of experiments with identical initial conditions, then this is called an set of ensembles. Okay, and averaging of this is called an ensemble average. So we are repeating an identical experiment for multiple times, taking the data at each time, and then we are doing an algebraic mean of those quantity. or we are taking an algebraic average of those quantities, and then that averaged quantity is called an ensemble average. Okay, so you have to perform the number of experiments over a, we have to perform a large number of experiments with the identical initial and boundary conditions, and then take the data. At each time we will get the different data. Okay, if we put the exact initial boundary conditions and identical and initial conditions, we will repeat the same experiment, but in actual scenario we can't put the exact initial and boundary conditions. That is not possible. So like the, when we are talking about the exact initial and the boundary conditions, we are saying that as far as it's possible to keep the boundary conditions and the initial conditions exact for all the experiments. Okay, but in reality there always will be some disturbance from the environment and some perturbations which we can't ignore. So because of those external factors only, that the result at each experiment will be different. So if I write it down, the definitions of an ensemble average, so then you can write it as something like a collection of independent, this is the definition, you can write it down, a collection of independent realizations of a random variable, a collection of independent realizations of a random variable obtained under identical conditions is called an ensemble. Okay, the ordinary arithmetic average over the collection is called an ensemble average. Okay, the ordinary arithmetic average over the collections is called an ensemble average. Okay, so here is the important point. So in a real experiment, what we actually do is the ensemble average. It's not the time average or not the space average, it's rather the ensemble average. Okay, so now we will talk about something which is that homogeneous and the isotropic turbulence. And okay, before that I can talk about two important things. Is that homogeneous turbulence is what? For homogeneous turbulence, the turbulent statistics are independent of positions. Let me write it down. Homogeneous turbulence okay. For stationary turbulence, the turbulent statistics are independent of time. Okay. Now, for stationary turbulence, the time average is equal to the ensemble average. For homogeneous turbulence, space average is equal to the ensemble average. For turbulence, which is stationary as well as the homogeneous, that means for which the time average equal to space average, then is equal to the ensemble average. Okay, if that is the case, then it is known as ergodic hypothesis. Okay, so this is the homogeneous turbulence, this is a stationary turbulence. So I'll write it down. For stationary turbulence, time average is equal to ensemble average. For homogeneous turbulence, space average is equal to ensemble average. For homogeneous plus stationary turbulence, for homogeneous plus stationary turbulence, time average is equal to space average is equal to ensemble average. And it is known as ergodic hypothesis. Okay, so so far we talked only about the uh, time average, space average, and the ensemble average, and we talked about what is the ergodic hypothesis. So for okay, before going into that, let me prove one more thing, is that so we know that the actual velocity u is have some average plus some u prime. Okay, now from here we can show that the average of the fluctuations is also 0. How? Let's take the average of that. So if I taking average, so I have u, so u average is equal to u average plus u prime whole average, and these I can write it as the sum of individual average. So this is average over average plus u prime of average. So what is the average of an average quantity? Will be the same quantity, right? The average quantity plus u prime average. So that means what I am getting from here is that u prime average is equal to 0. So that means the average of the fluctuations is equal to 0. That's why it is fluctuation. Okay, so and this is for any average, whether it's the time average or the space average or the ensemble average. For any kind of average, the average of the fluctuations is always equal to 0. Okay, like this is a very simple straightforward proof. You don't need to think much about that. Okay, is that fine so far? Okay, so now we'll talk about the homogeneous and the isotropic turbulence, but I think before that we can talk about something which is the correlation statistics. Okay, or as far as the averaging are concerned, we can have the moments of different averaging. So this is the mean or the average. So the mean or the average is the first moment. The second moment is called the variance. The third moment is called the skewness, and the fourth moment is called the kurtosis. So these are again like when we will go into the details of the subject, you need to deal with all these statistical description. Here we will not go into that. Okay, So yeah, I will not go into that. Okay, fine. So now we'll talk about the, so let me write it down. So I will have that. So what I have is that u is equal to u bar plus u prime. Okay. What is the deviation from the mean? Is equal to u minus u prime. Okay. So how we define the RMS of u? So the RMS of u is equal to what? This central moment. Okay, the first order central moment. Okay, so it is the u minus u prime square bar and the, so square then average then square root of that is the RMS. Okay, so in general for any nth moment thing. Okay, so what is the definition for the central moment? Okay, so the in general for any nth moment you can write it as u minus u prime, sorry, u minus, sorry, I wrote it actually wrong, so it should be u bar because it's the deviation from the mean. So this is u bar and this is also u bar. Okay, so this is basically, so what is u minus u bar? Is the u prime square bar. Okay, u prime square average of that. Fine. So in general for any nth moment, or let's say any mth moment, this u minus u average, okay, for the mth moment m, the average of this quantity, I can write it is in this form. So this is, if I write it in terms of the ensemble averaging, so it will be 1 by n, then average over all ensemble n is equals to 1 to n. This will be u at x comma t n minus u bar at x comma t n, okay, to the power n. So this is the averaging of that entire quantity. So that means this u minus u bar, sorry, why I am all the time writing u prime, so u minus u bar square bar is equal to variance. Okay, so this is actually the central moment primarily carry information about the fluctuations only, because we are calculating everything from the deviation from the mean, and the deviation from the mean is the fluctuations. So this is the variance of the fluctuations. Okay, so this is the variance of u, I mean the variance of the velocity. Okay, and this u minus u bar, the cube, then whole bar is called skewness. And this u minus u bar whole to the power 4 average of that is called kurtosis. Okay, fine. And this u minus u bar, the square root of that is called the RMS or the standard deviation, like this. Okay, so this thing is the second moment, the square root of the second moment is called the standard deviation. Okay, or the RMS. Fine. Now this averaging process doesn't completely explain the turbulent statistics. Okay, so in order to know the information about the temporal duration or the spatial extent of the turbulence, you need to know the correlations of the, so you need to know the correlation between different variables or the correlation of a single variables with itself at different times. That also we need to know. Okay, so now we'll talk about the correlations and correlation coefficients for turbulent flow. Let's talk about that. Correlations and correlation coefficients. So first let's define what is the correlation. Okay, so if I have two variables, let's say I will talk about in terms of u and v only, let's say, or ui and uj, or the u and v, whatever you want to call it. So let's say I have two different variables at two different locations at two different time. Okay, so let's say I have x at x comma t. Okay, so this is a random variable at location x and time t1. This is and let's say y, I have another variable y comma t. At location y and time t, okay, at location y and time t at time. So this is x1 and t2. So at time t1 and time t2 at two different time, not at the same time. So the correlation between the two, if I write it down, okay, that will be, so the correlation between the two, so x at time x comma t1 into y at time y comma t2 multiplication and then ensemble average of that, okay, it is the correlation between x and y. Correlation between the variable x and y, okay. Now if x and y are the same random variable, if x and y, if x and y are the same random variable, then the correlation between them is called the autocorrelation. Okay, then the correlation between them is called the autocorrelation. Fine. So in terms of any general thing, that is, let's say the correlation, if I write it in terms of r and r of I comma j, okay, see r of I comma j between two variables, which is ui at x1 comma t1 into uj at x2 comma t2. So u1 ui and uj are two variables, so then these things, the average over that is the autocorrelation. So r11 r22 etc. are autocorrelations. Okay, and r12, so I'll just write it in a formal way. So for I equal to j, Rij is called cross correlation. Okay, so for what quantities we need to know the correlations, that is the fluctuations of the turbulent velocity, okay, that we need to remember. So we only need to know the correlations of the turbulent fluctuations velocity. Okay, so for stationary turbulence, so that means that if I call about the autocorrelation of the fluctuations, so this u prime at t into u prime at t plus tau, okay, the average over this will be some r of tau. Okay, this is the autocorrelation of u prime. Okay, it is the autocorrelation of u prime, and these correlation coefficients this small r of tau in this case is equal to r of tau divided by u prime square bar. Okay, so this is correlation coefficients. So in generally the correlation coefficients are basically scaled normalized correlation coefficients. I mean the correlation coefficients are the normalized correlations. Okay, that we need to remember in this case. So this is the autocorrelation coefficients. This is the autocorrelation coefficient of u prime. Okay, now I can always represent the turbulence energy spectrum in terms of the autocorrelation coefficients. Okay, I can always represent. So let's say if my s of omega is the turbulence energy spectrum, okay, so s of omega is equal to 1 by 2 pi integration minus infinity to infinity e to the power minus I omega tau to r of tau into d tau. Okay, and this s of omega is called the turbulence energy spectrum. Okay, so this by inverse Fourier transform what is r of tau So this is from the time space to the frequency space. So these things is from the time space to the frequency space, and this is from the frequency domain to the time domain. Okay, so this is from the time domain to the frequency domain, the first one, and this thing is from the frequency domain to the time domain. it will be e to the power I omega tau s of omega into d omega. So that means this s of omega and r of omega are the Fourier pairs. Okay, they form the Fourier pair. So the turbulence energy spectrum and the autocorrelations, they actually form the Fourier pair. So that means if you know the autocorrelation of the fluctuation, then you can get the turbulence energy spectrum by the Fourier transform. Okay, that is why these correlations are important. Okay, so at time t is equals to 0, so here is an important fact that I need to think is that yeah, so this is my r of tau. Actually I can write down the fluctuations in terms of the energy spectrum. Like if I know the information about the energy spectrum, I can calculate the u prime square bar. That quantity I can directly calculate from the turbulence energy spectrum. So let me see how I can do that. Okay, so what is r of 0? S omega into d omega, am I right? That is the r of 0. Now at what is r of tau, what is r of 0, what is the definition of r of tau? What is, as we know that is again r of tau is equal to u prime of t into u prime of t plus tau, this whole average for t is equal to 0 and tau equal to 0. This r of 0 is equal to u prime square bar. Okay, therefore this u prime square whole bar is equal to integration minus infinity to infinity s of omega into d omega. So this is how you can actually show that the turbulence energy spectrum can be related to the fluctuation component of the velocity. Okay, that when the velocity fluctuations you can relate it. So now let's talk about the homogeneous and the isotropic turbulence. This is very much important. Like what is homogeneous and isotropic turbulence? So as I already discussed, the homogeneous turbulence, the homogeneous turbulence means the turbulence statistics are invariant under the translation of the coordinate system by which the turbulence statistics are described. That means the turbulence statistics are invariant about the translation of the coordinate axis. The isotropic turbulence means the turbulence statistics are rotation invariant of the coordinate axis. For isotropic turbulence, what will be the condition for isotropic turbulence? That means the turbulence statistics are direction independent. Okay, for isotropic turbulence, this u prime square bar average is equal to v prime square bar average is equal to w prime square bar average. Okay, that means the u, v and w component of the velocity, the fluctuations of that, and then square and their average are the same. Okay, so this is for isotropic turbulence. Okay, so I guess that's all. So in the next class we will derive the Reynolds averaging for the Rayleigh equations. We will describe and then we will stop the discussions about the turbulence. Okay.